Okay, in this video, I want to move on to the second part of statistical inferences, and that is hypothesis testing. A hypothesis is a claim or statement about a property of a population. Um, a population or a hypothesis test or a test of significance, as it's sometimes called, is a procedure for testing a claim about a property of a population. We need to first identify exactly what outcomes are going to be considered significant. In other words, unusually high or unusually low, that would be unlikely to end up with. We'll focus on understanding how the hypothesis testing procedure works and learn how to use the technology to do that heavy computations. You must be able to speak the language, use the technology, and interpret the results. So that's where our real focus is going to be. I do want you to understand the formulas because you're going to select the formula that is used, plug in the components, and then I will allow you for the test to use StatCrunch to do the actual calculations. But I do want you to identify the appropriate formula and plug in all the components. Okay, we're going to start out with this 8-step process to hypothesis testing, the first of which is identifying the null and the alternative hypothesis. So a lot of times when you're doing a test, you get yourself confused, like, oh, are we trying to prove that it's more than, that it's equal to some proportion or less than some proportion? This nailing down and identifying a certain structure to you, your null hypothesis and alternative hypothesis or your claim, is one way to kind of keep yourself organized. So this is the standard. The null hypothesis always includes an equal sign. The null hypothesis is usually notated by H of O or perhaps H of N. It's a statement about the value of the population parameter. In other words, the proportion is equal to, population proportion is equal to 20%, or population proportion is equal to some percentage in this case, because we're looking at proportion. But null is always the equal to. Now, the opposite of equal to is a couple other things. The alternative is going to be, the alternative hypothesis is denoted by H of 1, HA, or HA capital A. It is a statement that the perimeter has a value that is somehow different. So different would mean that it's not equal to, it's less than, or greater than. So one of these three signs are the options for the alternative hypothesis. So if it's less than, you're looking at in the left tail. If it's greater than, you're looking at the right tail. Just that'll make more sense as we move forward. Okay, so the textbook identifies these, I keep going the wrong direction on my arrows here, these 8 steps. I'm not a big believer in the first and the second because I think you could get yourself turned around. So very often I just dive right in, make sure that you guys know how to identify the null and the alternative. But you want to look and identify the claim, and try to put that in symbolic form and then give the symbolic form. But the big thing is that doesn't really matter if you can do that and not identify if it's the null or the alternative. So I'm going to do this all in one step when I do my examples. So you're going to identify the null and the alternative hypothesis, and I want you to recognize that both of these are dealing with the population proportion in this case, not the sample proportion that you're going to have in your problem. So the null and the alternative hypothesis have to do what we are projecting about the population. Okay. The next thing we're going to do is select a significance level, and that is going to be given to you in the formula. Either you're told the confidence level and you have to identify the significance level, or you're going to be told the significance level and then you need to identify the confidence level. If you were in charge of doing a research, you would spend a whole lot of time stopping and thinking through your type 1 and type 2 error probabilities. We're going to discuss that more as we do examples here. The really heavy number crunching comes into play in this 5th step where you are calculating a test statistic. You'd be using those formulas in a chart that I showed you earlier, but in each section I'll show you the specific formulas that we'll be using. Okay, so once you've done all that, then you have one of 3 methods that you can use to evaluate your outcome. When I do my examples, I'm going to use all 3 methods, just so that you can see how they all should support each other. And actually in the proportion method, there's really only 2 methods, the p-value and the critical value method. The confidence level or confidence interval should support these as well, though. So I do all 3 no matter what. Okay, so the p level is basically the probability of getting an outcome this significant. because when you're calculating that test statistic is a z-score that is associated with that data. And so you want to know how significant that is. And that p-value is going to give you that. Okay, the critical value is where you're plotting the test statistic as well as the critical value on the normal curve and trying to figure out which one's more extreme. If your test statistic is more extreme, that's really unique, and you're going to say that you would reject the null hypothesis, that you have a statistically unique outcome. And again, as we get going, you'll have more practice with this. Then you're going to make a decision. And again, your decision is going to be reject the null hypothesis or fail to reject the null hypothesis. That sounds very techy, but basically when you're saying reject the null hypothesis, you're saying that, hey, we have an outcome that does not support our null hypothesis. We have something unique. So you would reject the null hypothesis. If you're saying fail to reject the null hypothesis, you're saying that, hey, our data isn't any more unique than our critical value. This data doesn't give us anything significant here. So in that case, you would say fail to reject the null hypothesis. Okay, because step 7 can be kind of confusing, number 8, you are to restate that decision in non-technical terms. And so you might say the evidence supports the claim that DMAC students have a higher proportion of tattoos than non-DMAC students, whatever it might be. That's just an example. So you would restate this decision in terms of the problem. Again, we will practice all of this stuff. Now, again, the confidence interval we cannot use for proportions, but we can use it as a check just to kind of support. The confidence interval, you have to remember, is a two-tailed event, and it's going to tell us where we think the population proportion would likely fall. Well, if we are 95 or 90% confident that the null hypothesis is in this interval, you can't possibly reject the null hypothesis. So you reject the null hypothesis if that population parameter is not in that confidence interval. We touched upon that a little bit when we were talking about confidence intervals. Okay, so back to the p-value. That p-value is that probability of getting a test statistic that is at least as extreme as the test stat. So it's out there in that rejection zone. So there's this chart here. Basically, you can follow the chart here. This falls into place very well and is helpful if you're using the z-table. When we go into StatCrunch, you're going to find the whole statement of reject the null hypothesis, or if the p is low, the null must go. I will come back to that in just a little bit. But if you're using the table, you would have to double the p-value from that table to tell you the probability that are in both tails. But if you're doing a left tail test or a right tail test, you're only looking at that one tail, and the p-value that you get from the table is the correct from one tail. So I want to make a note here. Please be careful. Do not confuse these different notations that all include p. I will try always to include a capital P when I'm talking about the p-value, and to include the word value there when I'm talking about the p-value. P hat is our proportion derived from our sample, and P, without any markings at all, cursive looking P here, is our population proportion. We're using our sample proportion to make inferences about the population proportion, seeing if we can learn or make any projections about the true population proportion. Okay, so that critical value method requires you to compare the test statistic derived from our sample data to the significance level or to the critical value. So it's helpful to draw the curve and put your critical value, that z-score that we pulled from page 4 of your notes, I believe, comparing that critical value to the test statistic. Put them on a curve together and see which one's more extreme. If the test statistic is more extreme than the critical value, it's in that rejection zone, which means you would reject the null hypothesis. You have something unique there. Okay, so this is the formulas that you would be using for this, the next two sections, but we're going to be focusing right now just specifically on proportions. The test statistic is this formula, p hat minus the population proportion, divide by the square root of pq, divide by n. This is using the p and the q from the population proportion and is therefore an estimate of the true population proportion, standard deviation. So again, this is kind of a mix of p hat, p, and q. Notice in this, underneath this radical, for the test stat, we do not have any hats. We're going to be using the normal distribution curve that you'd be plotting this on. And again, you need to have the requirements that we have 5 successes and or 5 failures, one or the other. Okay, and that has to do with having an appropriate sample size. All methods, again, are going to be equivalent when we're dealing with means and standard deviations and variances, but the confidence interval method could produce different results than the p or the critical value method when you're dealing with proportions. I will not give you any scenarios where it is different, but that difference could evolve from the fact that when we're calculating our confidence interval, we are using, instead of using p and q, we're using p hat and q hat from the sample. That's totally the reason there. So, but I'm not going to give you any scenarios where it does have a different outcome. So again, the final, I guess the 7th step is to make a decision to reject the HO or fail to reject HO. So I want you to, again, really wrap your head around this whole idea that we use the term fail to reject and reject because we don't ever want to say that we accept or that we don't accept the null hypothesis, and we certainly don't want to say that we prove the null hypothesis or fail to prove the null hypothesis, or that we prove the alternative. We never prove anything. Our statistics comes from a sample, and it's just saying this sample doesn't support the null hypothesis, or it doesn't reject it. It shows evidence to support it. You know, if we're saying fail to reject the null hypothesis, we're saying that our statistic actually supports, our test statistic actually supports the null hypothesis. So you kind of have to wrap your head around the verbiage there. Okay, type 1 and type 2 errors. I really need for you to memorize these two. Type 1 error is the mistake of rejecting the null hypothesis when it is actually true. And that is the case when alpha is too large. Okay, type 2, the mistake of failing to reject the null hypothesis is when it is actually false, is the case when alpha is too small. Our rejection zone is too small and that we didn't capture the fact that we have something that is significant. So you need to kind of keep those two things straight. Here we have an example. Given the claim that a medical procedure designed to increase the likelihood of a baby girl is effective, so that the probability of a baby girl is greater than 50%, 0.5. Okay, our HO and our HA, H1, another notation there for HA, or alternative. HO, again, has that equality sign that the probability of having a girl is 0.5. So probability, the population proportion is equal to 0.5. The alternative is that the population proportion is greater than 0.5. That's where our claim happens to be. Okay, type 1 error is the mistake of rejecting HO, that the population proportion is equal to 0.5 when it is actually true. And we made the mistake of rejecting. Type 2 would be the mistake of failing to reject HO, which is the population proportion is equal to 0.5, when it is actually not true. Okay, so basically the decrease of one involves an increase in the other. That's one way that you can think of that. Okay, so I want to go into applying this to proportions and really start talking about the formulas. Then we'll have a couple of examples. Okay, so testing the claim about a proportion, again, testing the claim about a population proportion P, we need to use the p-value method or the critical value method. Confidence intervals can be used to support, but could be somewhat different. Therefore, the confidence interval is good to estimate if you have no other, no claim to go by. But if you're testing a claim, you really should use the p-value or the critical value method. So our notation, N and P, I think we're all good with. We've used that before. P hat, we know the number of successes divided by the total. Q would be 1 minus, it's going to be the complement of the population proportion. So we'd need to make sure that we understand those notation pieces in order to use this statistic. Again, our requirement, simple random sample, fixed number of trials, that is your N. The trials are independent. There's two different outcomes, either success or failure. And then we have the probability of success remains the same for all trials. And then we have at least 5 successes and or 5 failures. Our critical value method, again, you're comparing the test statistic to the critical value method. Or to the critical value. The p-value method, you're comparing that p-value, the probability of getting that test statistic, to alpha. This is a hugely important statement. I wish I would have highlighted it here. I would encourage you to do that. Compare the p-value to the test statistic. Compare the test statistic to the critical value. That's what you're doing in each of those two things. Again, on the p-value method, you're going to need to double the p-value from the table if you're doing a two-tailed test. I think for the most part, you're probably going to be doing this in StatCrunch. So these are explanations of the p-value given if you're doing a one-tailed test or a two-tailed test. The p-value, if it falls over here in one of the, less than the alpha, the critical value, it's going to be lower than alpha and it's in that rejection zone. If p is higher, it's going to be in this usual area because the test statistic is between these two critical values and it's going to be usual. Okay, so in a nutshell, if the p is low, the null must go. So if the p is low, the null must go. That would mean reject null hypothesis. If the p is high, the null will fly, and that would mean fail to reject the null hypothesis.